all objects fall at the same rate in a gravitational field regardless of their mass. The Einstein Equivalence Principle states that inertial and free-falling systems are entirely equivalent. In such laboratories, there is no experiment of any kind that is capable of distinguishing between inertial and free-falling motion. This is because the Einstein principle of equivalence declares that the acceleration of a free-falling laboratory completely cancels out the effect of gravity, not only dynamically, as in the weak equivalence principle, but also in any conceivable experiment in any branch of science. Therefore, special relativity, and not just Newtonian mechanics, may then be used in free-falling systems as well as inertial systems. There are only a few limitations to the Einstein equivalence principle. Well, the main one is that the experiments conducted can't be ones that involve self-gravitating properties. We'd need to test electromagnetic interactions or, say, the weak nuclear force interactions. Indeed, one main motivation for the Einstein equivalence principle, or just EEP, is in trying to integrate the theory of electromagnetism into the framework of gravity. So let's get into the details on this. What is now called the Einstein equivalence principle states first that the weak equivalence principle holds. Then, to complete his work on gravity, Einstein included two more ideas into his form of the equivalence principle: local Lorentz invariance and local positional invariance. Local Lorentz invariance means that no matter how the experimental laboratory is freely falling with respect to the ambient gravitational field, inside the laboratory frame, all experiments done in that frame will be measured as in an inertial frame. In other words, the outcome of any local non-gravitational experiment is independent of the velocity of the freely falling reference frame in which it's performed. This is exactly like being down in the hold of Galileo's boat. Now, in addition to sailing on a glassy sea at constant speed in one direction, we can now surprise poor Galileo by dropping his boat from a great height, or sending him flying into space in orbit around the moon. Such a spacefaring, freely falling Galilean boat might have floating fish and water droplets hovering stationarily in the air, or, as we see Commander Scott Kelly aboard the International Space Station, one can juggle balls by simply placing them where you want them to be. They'll just stay there because they're simply falling at the same rate as everything around them. But as the ISS goes around the Earth at 90 minutes per orbit, it experiences changes in the gravitational field. Other than the tiny effects due to non-uniformity of the gravitational field, Commander Kelly's experiments aboard the ISS are a nearly perfect inertial reference frame. The speed, altitude, and direction of the ISS through the Earth's gravitational field doesn't affect, except at tiny levels, the fact that it's fully equivalent to the ISS being deep in space, far away from any gravitational field whatsoever. In many ways, the concept of local Lorentz invariance is essentially where special relativity gets integrated into general relativity. It's truly astounding the scale and amount of experimental support for special relativity that has led it to being central to all physics. The vast supporting experimental evidence for the local Lorentz invariance includes, of course, the classic Michelson-Morley experiment, and tests of time dilation by Eves and Stilwell and Rossi and Hall, tests of whether the speed of light is independent of the velocity of the source, using both binary X-ray stellar sources, where the source of photons is coming from an accretion disk around a stellar mass black hole, and secondly, high-energy pions impinging on the Earth's upper atmosphere in cosmic rays. There are also numerous tests of isotropy of the speed of light, which would of course violate local Lorentz invariance. In addition to these direct experiments, advancements in quantum mechanics have cemented local Lorentz invariance via special relativity's integration. Specifically, Dirac's equation predicted antiparticles and quantum spin, which then spawned the stunningly successful relativistic theory of quantum electrodynamics. In 2024, 119 years after the introduction of special relativity, it is actually safe to ask what is there left to test. Special relativity, and therefore local Lorentz invariance, has been so thoroughly integrated into all modern physics that its validity is rarely challenged except by cranks and crackpots. Interestingly then, since the early 2000s, legitimate theoretical and experimental efforts have been undertaken to find violations of special relativity. This is because the promise of quantum gravity theories to seek new physics that extends Einstein's relativity. This doesn't mean relativity will be replaced or invalidated, but it means that new interactions yet unseen remain to be revealed. Such models predict apparent or effective violations of Lorentz invariance. Quantum gravity, in general, asserts that there is a fundamental length scale given by the Planck length, which is 10 to the minus 35th meters. But length is not an invariant quantity due to special relativistic length contraction. So there might be something there to seemingly violate local Lorentz invariance. Next, in a brane world, with our universe embedded in some higher dimensional bulk, like we saw in the movie Interstellar, the confinement of normal physics interactions to our four-dimensional brane could induce apparent Lorentz violating effects for us, while leaving it locally invariant in the higher dimensional bulk world. And finally, string theory or M theory suggests effective or apparent violations due to the existence of new and additional scale, vector, and tensor long-range fields, which couple to the normal matter. This last one's getting way ahead of ourselves, though. Let's now look at local positional invariance. This means that no matter where or when in the universe we put our laboratory frame, there won't be any difference between the frame's measurements. This has huge implications for physics. One of the most important results is that the physical constants of nature, such as Newton's gravitational constant and the fine structure constant, are not functions of space and time. They don't change. This means they are profoundly elemental to the physics of our universe. Of course, this is going to lead to some very interesting tests, which I'll talk about later. Here, the local in local positional invariance and local Lorentz invariance means that the experimental setup in the laboratory must be small compared to variations in the gravitational field. These, of course, would be the tidal forces, and the test experiment must be small enough so that the gravitational potential does not alter the result. Just adding the constraints of local Lorentz invariance and local positional invariance, Einstein was able to predict the gravitational redshift, which has subsequently been observed. Theories of gravity that obey the Einstein Equivalence Principle are forced to be what we call metric theories of gravity. Such theories mean that all freely falling bodies follow trajectories that are things we call straight lines in curved spacetime, geodesics. I'll get into the definition of a geodesic later on in this video, but suffice it to say that it's the shortest distance in a curved spacetime. So to recap so far, the differences. In the weak equivalence principle, we have that the inertial mass and the gravitational mass of any object are equal, or, equivalently, in small enough regions of spacetime, the motion of freely falling particles in a gravitational field are identical to motions in a uniformly accelerated frame. In contrast, the Einstein Equivalence Principle states that, in small enough regions of spacetime, the non-gravitational laws of physics reduce to those of special relativity, and it's impossible to detect the existence of a gravitational field by means of local experiments. Gravity then couples not only to rest mass, like the Leaning Tower of Pisa of Galileo, but also to all forms of non-gravitational energy and momentum, such as the electromagnetic binding energy of atoms and molecules, and makes any experiment useless to test the difference between an inertial frame and a freely falling frame. And now let's see how we can take it a step further.